Okay, reading number 8 on cycling biomechanics is kind of a blend of reading number 7, which was on road bicycle fit, and some of the earlier readings on modeling and simulating cycling with computer models and mathematical models. In those earlier studies, we had a model of a bicycle slash rider that looks something like this, and there's some muscles that span the joints of the bike here, the hip and the knee and the ankle labeled there, and then we'd optimize the excitations of those muscles to get the rider here, the simulated rider, to turn the crank in a way that minimized metabolic cost or various other performance factors in cycling. So optimizing the pedaling biomechanics of the rider for a particular performance-related goal. This study blends that approach with the bicycle fit approach here described in the previous reading, the Silberman et al. Reading on road bicycle fit. As you can imagine, and something that you might get the sense of as you're reading over reading number 7, the Silberman paper, is that there's a lot of factors to consider here, and that they likely interact in really complicated ways, or really non-intuitive ways. Like if I change the seat height for a particular purpose, that might also change how I'm interacting with my pedals in terms of my cleat position. And so maybe now I need to adjust the cleats a little bit. And maybe now I adjust the cleats a little bit, but now my stem's a little bit too high or a little bit too low, and I need to play around with that a little bit. So it all becomes very complicated and kind of interrelated, and a lot of trial and error involved here, and is very much dependent on the skill and intuition and experience of the trainer or the coach or whoever's doing the fitting, and kind of a subjective feedback loop there with the rider in terms of what feels good, or when you go out and race, how does this feel? Are you performing better? So kind of at least hypothetically and often in practice, a very long and time-consuming process. The approach that they forward in this paper is a more objective, faster way of achieving that goal of determining the best fit of a bicycle rider for a particular performance goal. Here, they were focusing on maximizing economy, which they defined as achieving a particular pedal output or a particular crank power while minimizing the muscular effort required, which they used here as a quantifying muscular effort by minimizing the torques that the muscles had to produce around the hip and the knee and the ankle joints to turn the crank with a certain power output. So kind of an efficiency-related goal that might be beneficial for, say, long-term cycling, like cycling a long-distance race. What they optimized here was not just the control of those joints, influencing the torques on the joints, but also the geometry of the bike. In particular, they were optimizing the length of the crank, the height of the seat, the angle of the seat tube, which is this angle here of the piece leading up to the seat, and then also the position of the cleat on the foot. Okay? From this, they then determined the values of those parameters that minimized their objective function here. That's a term that you see throughout this paper, the objective function or the cost function, which was what they were trying to minimize. So optimizing the fit of the bicycle, those 4 geometric parameters of the bicycle, to minimize the torques on the joints produced by the muscles in order to complete the pedaling motion. Okay? And through this, it was technically successful, and they were able to determine the optimal parameters in terms of the fit of the bicycle that minimized the torques needed to pedal at a rate of 200 watts, I believe, was the power output that they simulated here. They say this would be equivalent to cruising over flat ground at about 20 miles per hour, which is a pretty decent pace over flat ground for an average cyclist. Okay, this will be a short one, not a whole lot else to say about this one, but this is kind of the vision of sports science, the blend between sports science and computer modeling and biomechanics in a lot of fields, in a lot of sports, not just cycling, but in a lot of sports, where we take something like this, which is just kind of a general model, a proof of concept, and then define that model on a athlete-specific basis, rather than using generic parameters here for like the geometry of the legs and the strength and power of the muscles. Taking measurements of those things on a real cyclist and tuning the model specifically to them, tuning the range of possible fit parameters on the bike specifically to their bike or to their options for bikes, and then optimizing that fit and the pedaling technique of the rider to achieve certain goals, whether it's maximum power output, or whether it's economy, minimizing metabolic cost, or whether it's minimizing the load on some joint of the body or some part of the body that's injury prone for this individual, or some combination of these things. What's the best trade-off for general performance? Some combination of, say, injury avoidance and performance in terms of power and performance in terms of aerodynamics. Lots of different sports where that could feasibly apply to. It hasn't yet been applied in practice in too many situations, and certainly isn't like standard practice in any sport in modern times that I know of, but a lot of potential for this to someday make major contributions to sports. So kind of a practical application of the computer modeling realm of biomechanics that can often seem to have not real obvious practical applications a lot of the time. Not yet something that's done in modern times. This is a 1989 paper, wasn't common back then, certainly isn't common in practice now. But cycling, I think, is an example of a sport where this is some fairly low-hanging fruit. It's relatively accessible to actually do this in practice in cycling compared to some other sports. Okay, that is it for this time. We will see you next time.